Good evening, ladies and gentlemen. We are here in the Eötvös University Faculty of Science, Department of Petrology and Geochemistry. And especially we are visiting now the Cosmic Material Space Research Group. We are that space research group which launched the lunar petrologic thin section set from NASA, and also we learn the Antarctic meteorite thin section set from the National Institute of Polar Research, Tokyo, Japan. This evening we deal with the solar system materials, especially meteoritic materials, lunar materials, and for comparison some terrestrial materials, and we have one thin section from the Mars too. So finally we shall study the possibility of the life on the Mars. Now we begin with the crystals themselves and the solar system. We know many rocks from the Earth. We can see the details if we observe them by a loupe. In many rocks you can see the crystals themselves, but as far you cannot see the crystals, only the large blocks, the large boulders of the rocks. For example, we remember the great blocks of the limestones or great basalt orgels, that kind of rocks we know from Hungary at the Lake Balaton, the so-called Badacsony. It has a very beautiful development, a very beautiful shape, hexagonal shape in cross-section, and they form great columns standing above the lake when you are approaching in a ship. Now we deal with the solar system minerals which compose these types of rocks. Not many type minerals consist of in lunar and meteoritic rocks. We shall study them in the solar material which origin from the beginning of the solar system. So the first part we deal with an average overview of the solar system. Solar system consists of the Sun in the center and the planets. I take only dots here because instead of planets I will show the minerals. Why minerals? Because minerals represent temperature. What temperature? All minerals, when we go far from the Sun and with the increasing distance, the decreasing temperature changes the minerals which were precipitating at the beginning when the solar system was formed. The early solar eruptions, you can see recent eruptions in this NASA photography. The early solar eruptions were large and even the minerals were melted. But what were the minerals when the solar system was formed? In the solar nebula, temperature determined the precipitating minerals. In the vicinity of the Sun, 2000 degrees Kelvin, far away in the Sun, over in the vicinity of Pluto, 50 Kelvin degrees, determined the precipitating minerals, and we can draw here a sequence of minerals beginning with refractories. For example, corundum. Here is the chemical composition. After corundum, the nickel iron metal was an important precipitating composition, and then came the silicates, of which olivine, pyroxene and feldspar are the most well known. Pyroxene and feldspar are the main components, and we shall meet with them in meteorite test. Then came a period, a distance, an interval where different minerals contained water. Before them, there was an iron sulfide, the well-known pyrite is a mineral well known in the earth. Then there is a sharp but invisible line here, and then came different asbestos minerals. For example, this is the serpentine, tremolite. Over these minerals, the most important mineral and crystal, not only the whole solar system but the whole world, is ice, water ice. This is the distance. It is a little bit farther, the 50 degrees. Now I run out from the space. This is the place where Jupiter was collected, accreted, because the most important chemical element is hydrogen and oxygen, not only solar system but all over the universe, and that's why where the great mass of this mineral precipitated, the greatest mass of the planet could also accrete later. In this vicinity we find Jupiter and Saturn. These are the medieval age old symbols of these planets, and at the same time over these minerals I will assign the planets. Here inside is Mercury, then came Venus, then the Earth, and then is Mars. And here is the asteroid belt, and came Jupiter, Saturn, Uranus, Neptune, Pluto, and you can see that from this mineralogy in the deep, we know that some of the planets have atmosphere, and mainly icy material in the outer solar system. This is the composition we shall study, but mainly the inner solar system, because we know some fragments of Mars, we know some fragments the Earth's moon, and many fragments from the asteroids in the form of meteorites. Meteorites are very important fragments because they tell the evolutionary history of the planetary material, and this is the topics we deal with in this evening: the evolution of a planet, evolution of a planetary material, because we shall look for the place where could survive the ancient material, that kind of material which can be found in the meteorites. This is the first program part. We shall study meteorites, ancient forms, ancient structures and their transformations. We first begin to study Antarctic meteorites. It is an interesting story. How did they arrive to Budapest as one from the Japanese polar expeditions, which began in 1969. They studied Antarctic surface, which is covered with ice. Ice is moving toward the shoreline, but imagine if there is a sharp mountain in front of the flowing ice. Here is the sea, and blocks are fragments swimming in the sea. When the moving ice toward the shoreline has an obstacle, it begins to evaporate on the surface. Inside the ice, there are meteorites. Some 1,000, some 10,000 years ago, from the inner Antarctica, they were embedded into the ice, moving to the shoreline, but in this place they begin to come up and they remain on the front of the mountains, not only in the mountains, not only at the front of the mountains, but at the places where the subsurface mountains came near to the surface. Because here you can see also upstream of the moving ice. And that's why here and at the obstacle you will find many meteorites. That's why that in Japanese collection, I think now in 2001, there is about 14,000 pieces of meteorite. That some is paired, in average 10 is paired. So we can see that it is about 7,000 meteorites. No, 10 is paired, so it is 1,400 meteorites. And almost the same is in American collections. So almost the same number of the meteorites exist from polar collections than which will fall in any other continents of the well-inhabited places all over the world, in countries where they were collected. Now these meteorites represent an early solar system fragments, because in about 90% of these meteorites, small bubbles, small grains can be found. Its name is condrule. Condules are about 1 millimeter in diameter, but they are smaller sometimes. They may be 100 micron or 10 micron, so grow up, it is 1000 micron, and may grow up as 1 to 3 millimeters, not more. Sometimes these grains, these chondrules, were molten droplets of some silicate material, and we study now these materials because they represent ancient structure. When we take one thin section into the microscope, the 30 micron thick thin section, then we can see the structure inside, and now I will sketch one or two of these minerals. We can see these minerals in the condules, which I shall draw. 5 different types can be distinguished of these condules, and these 5 different types can be found the most ancient meteorites. One is the glassy. The glassy condules has no detailed structure. The next is the excentroradial. Excentroradials show a characteristic pattern. A needle-type minerals grow inside, and they are sometimes parallel. Maybe the molten material was overcooled, and suddenly some impression, some pressure, some collision made it to crystallize. The next one is very characteristic, the so-called barred structure. Bars of olivine crystals are formed inside, almost parallel. Sometimes 2 systems of parallels consist in, and some iron droplets also are arranged in the vicinity, and sometimes they are surrounded another belt of well-mineralized structure. These are the so-called barred condules. The next one is a porphyritic. In these olivine crystals with idiomorph or euhedral structure consists of the condrule, and between them some glassy material can be found. And finally, there is a granular type with many special subclass. For example, I draw one when the crystals are pyroxenes, and the pyroxenes contain some olivines in a poikilytic structure. It is a very interesting and rather frequent structure of the granular condyles, that they are poetically enclosing maybe inside some olivine crystals, and those olivine crystals that mainly from pyroxenes are composed. Why I explain so much about these condyles? Because these structure can be followed at the stages of this meteoritic material when it became transformed. Metamorph processes, the heating up of the small body, caused transformation and finally the destruction of the structure, and now we shall follow in details this process till the transformation of a small body toward a shell-type evolved asteroidal body, and this will show an example how the evolution, the thermal evolution, could change and arrange materials even in a small asteroidal body. So we shall study this process, and then we turn toward the NASA lunar samples. Now we begin to study these transformations in asteroids. In 1967, a famous paper appeared about meteoritics. This was the paper of Van Schmuss and Wood, who studied the structure, the matrix and mineral structure, the thin structure, texture of chondritic materials, of the 90% of the falls of meteorites. This structure is characterized by this chondritic structure, and this chondritic structure very well exhibits the types of condyles I showed earlier. But this structure gradually decreases, gradually diminishes, gradually will be lost when we heat up the rock. What is the heating inside in an asteroidal body? In an asteroidal body, the radionuclides heat up even the smaller, think about 50 kilometers in diameter asteroidal body, or a larger one, 100 kilometers in diameter. In these asteroidal bodies, the heating up gradually changed the inner structure. And Van Schmuss and Wood showed that initially the texture can be distinguished and separated gradual steps. They call them with numbers. Type 3, type 4, type 5, 6, we deal with these. And in this gradual sequence, only texturally we can see that the condyles are sharp. Later, condyles have some transformation at the edges. Step by step, the structure transforms and obscure. Finally, we can hardly, but we can recognize, we can discover that sometimes there were some condyles. And finally, and this is a new stage, a new period, which was very frequently found in Antarctica, more frequently than earlier. This is the so-called primitive achondrite. Primitive achondrite means that A in Greek, without condyles. So finally, we have a kind of dictar, a kind of almost granular and almost equigranular texture, which in the case, for example, Acapulco, a very famous Acapulco from Mexico, is this type, or Lodran is also this type. So that type of meteorites can be found here, which show that the differentiation begins in the asteroidal body. So we have a metamorph sequence of different textures in which the structure of the chondrules we have seen earlier gradually cease, gradually diminish and obscure, finally cannot be seen, and this begins a new period in the asteroidal material because two kinds of melting begins in such types of granular texture. One type of melting produces, we could see, iron, and iron will step by step together. Iron is a metallic type and the sulfidic type. When they are together, they have lower melting point, and they step by step go down and collect in the core of the asteroidal body. But another component is also not so far in temperature, because the asteroidal matter was heated up 1000 or 1100 degrees. Then basaltic material also come up to the surface of the asteroidal body. These are the basaltic achondrites. Basaltic achondrites on the surface, there are some types of them. In the bottom there are the iron meteorites. They came up from the deeper region, and they are some transitional meteorites, for example pallazites. They contain olivine grains inside the melt, inside the metallic melt, and it was frozen. And we have some residual material. Sometimes Lodran is considered residual material, but the most characteristic is ureilite. Ureilite is the most similar to the terrestrial mantle materials, because finally it is composed mainly from olivine and pyroxene. So we can divide two periods of the asteroidal history. First part is the chondritic history, and now I will show you the cross-section of the body. Now in this case, when we have gradually 3, 4, 5 and 6 types of the chondritic texture, then we have a corresponding cross-section shells. Outer is the 3, next is 4, 5, and inner is the 6. Vanchmus wood type. Inside a shell-like or onion-like asteroidal body. But if the evolution went forward, then we can see a more differentiated body, because we can see that the iron is moving to the center, so an iron core begins to develop, and at the same time the basaltic melts not so far from the surface go up. This is very rare. We know only Vesta, asteroid Vesta, which has such basaltic achondritic crust. So finally we can see that differentiated asteroids represent the planetary, the small body evolution, the thermal evolution, where differentiated materials can be found, and this differentiated material can be collected in these meteorites, and thin sections in the Japanese meteorite collection very well show and can be studied even by students, that this evolution step by step how formed different meteorites. Of course, there is a great variety of meteorites, and we know the different initial conditions, named E, H, L, and many types of sea carbonaceous chondrites represent different stories, but the main line of the history in an asteroidal body thermal evolution contains these main two steps. First, the onion shell-like structure, then a more differentiated structure with the branching of many types which form many layers inside the asteroids. This is the first and very clear event when we see an overview of it, and now we shall study a later story in the form of the lunar rocks. Now we study the moon. Two parts. The first part represents the classical view we could see in the nice spring evening. Full moon. Full moon shows large, dark, circular spots, which were named seas. In Latin word mare. The names Mare Imbrium, for example, means the sea of rains. There is a great ocean of storms, Oceanus Procellarum. Then there are some sinus medii, nebulas, then there are humorum, and there are tranquility, where the Apollo 11 landed. So many interesting objects can be related to the mare. And there is another surface where there are a lot of craters. It is lighter, mare darker. Terra is populated more with craters, and mare are less populated. So there is a difference between the two units, and in classical geology it is very important to map, to identify that kind of layers on the surface of a planet which can be distinguished. Now we can distinguish mare, dark, less crater and lower, and terra, more crater, lighter and higher. So this distinction makes a kind of basic stratigraphy. We can distinguish the more simple stratigraphy, a kind of column, a kind of pyramid, higher layer, lower layer. Higher layer is mare, lower layer is terra. And in the 1960s, the US Geological Survey, USGS, began to study in details the stratigraphy of the moon. Eugene Shoemaker is the main man, and Don Wilhelms, Hackman, and many others. I only wanted to mention people because they studied a very important central part of the moon, and they identified important objects. Copernicus crater, Eratosthenes crater, and here is the Apennine, Carpathians, Apennines, Caucasus, Alps, and so on, Jura. Many names from the terrestrial. Here is Altai Mountains, so very well known terrestrial geography, but the craters were named great scientists. For example, here is a very important crater. In full moon, a ray system is coming out from crater Tycho, from Tycho Brahe, who was very important observer and lived in Denmark, in Copenhagen, and later moved to Prague and became the royal astronomer of Rudolf II, who was also Hungarian king. We must know some history in connection with the lunar science too. Now, the lunar stratigraphy used the principles which were founded by important English men, scientists, for example, Lyell and Smith. I mentioned them most important work were basic in the end of the 18th century. The most important principle was that of Steen, also from Denmark. It is interesting about at the turn of the 16th and 17th century, about at 1600, the principle of the stratification, the principle of the sedimentation and the settling of the layers one above the other. Upper is the younger, on the bottom is the older layer. Using these principles on the moon, there was made a geologic map of the moon, and this shows that kind of blocks of rocks which are on the surface. Of course, these blocks of rocks belong to forms, crater forms, great impact forms, has outer rings, and these rings form great kind of chain of belt, but it is not in classical terrestrial sense a chain, but a form, a belt which surrounds the inner large plate. And we can see another important structures, but these impact structures are the most important in the moon, and these are the forms to which the surface layers can be connected. Why? Because going from up to down, we shall get a better pyramid of the layers. Up in this pyramid is the Copernican layer, because the Copernican ray system, like similar to Tycho, overlap everything, and this is the highest strata level on the moon. We can see in full moon case, everywhere you can see, almost everywhere you can see the ray system of Copernican type. Of course, Tycho is also Copernican type. The second layer from the top is Eratosthenean system. They have no ray system, not the ejecta blanket can be seen only in the vicinity of the crater itself. That is the second layer in the new system. So, Copernican system is the first, Copernican system, then is Eratosthenean system, then came the Imbrian system. At the beginning, Oceanus Procellarium was the main, but later the mare flooding and the impact and the formation of Imbrium was very near according to the crater counts, and that's why now we call the third layer Imbrian system, Imbrian layer. Then the Preimbrian was divided because the Nectarian system could be identified. The ejecta blanket of the Nectarian impact can be seen as Janssen formation. This is important when a great pre-mare basin was formed, then the ejecta blanket surrounded very large part of the vicinity of the central impact, and this layer was named as very important formation. Orientale cannot be seen only at the edge, has the Hevelius formation. Imbrian system is composed of Appennian and the Framauro formation, where Apollo 14 landed, and is the Janssen formation. These are very important great layers which form the stratigraphy of the moon. So Nectarian system, Nectarian and Prenectarian closes. And we can see the role of the lunar rocks, because this is a relative stratigraphy, and by the lunar rocks we can correspond absolute ages by radioactivity to these layers, and when we know this, we can compare how the lunar history is in between asteroidal history and the terrestrial history, because the asteroidal history is about some 10 millions of years of heating up, and cooling everything. We shall see that the lunar case is about 1.5 billion years in English meaning, but we in Europe we use for 10 to the 9 the milliard years age. So that's why we call eons. So 1.5 eon is the distance, the time interval of the evolution of the moon, while the Earth is 4.5 eon or milliard age. That's why we shall see the distinction between these layers. But before we study lunar rocks, we first correspond two main rock types to the dark and the lighter one. Darker one are basalts, we can study in the Earth too, and the lighter one we shall see they are anorthosites, and we shall study them and correspond the ages in the microscope. So now we turn our attention to the NASA lunar thin section and this macroscopic disk set. There are two main rock types which we can see in the disk. The disk contains the anorthosites, which can be corresponded to the lunar terra. Lunar terra, this is the far side, for example, of the moon with the Tsiolkovsky crater. They are fragmented with lunar craters. There is another important, the basalts of the great basins, and the mixture of different rocks during impacts. The third type is the breccia, and there are three different types of soils, of which the orange soil is the most interesting. Now we can see these materials in thin sections. It is interesting to see the thin sections, especially in the case of the basalts, because we can see some interesting crystallization sequence also for basalts. Basalts flooded very great distances. In the case, for example, in Mare Imbrium, Apollo expedition discovered that there are some floods almost 1,000 kilometers distance in Mare Imbrium, and it is interesting because in terrestrial conditions such kind of great floods were in very old times, about 3 million years ago, when comatids, very good floating materials, floated in the Earth. In the case of lunar basalts, imagine that there is a lava flow 5 meters thick, and you may imagine that the crystallization is different on the bottom than on the top of this layer, and this crystallization sequence can be studied by these lunar samples because there are three types of basalt. One basalt is from the top region, some from the middle, and one from the bottom. And I will show you some from the middle and from the bottom. Basalts are composed three main minerals in the case of lunar rocks, in the case of terrestrial rocks also. The third one is the black ilmenite, which is a magnesium, which is a titanium and iron containing oxide. But the most important is the pyroxene. This is a little bit pale brown in this picture, and there is twinned, and in the cross section, in the polarization microscope, in this section they are gray, and they have streaks because of the twinning. This is the very important and interesting Apollo 17 and Apollo 11 basalts, which contain very high titanium content, And also very high titanium content is that of the orange soil. It consists of small beads, like we know from the chondrules, almost the same size, about 100 microns. But they have the nice orange color because of the high titanium content. These fragments developed when a lava fountain spread away these droplets and they precipitated, and Apollo astronaut observed it is, have a look at, there is some color material. This is the orange soil, the only color material on the moon. It has a very deep source. It was found by scientists that it came from 100 or 200 kilometers deep and preserved the ancient characteristic of the lava, of the melt. So they represent some primitive material. But these rocks in the bottom of the lava flow sometimes are such gabbroic type, but this gabbroic type material is also important component of the terra. Terra is composed of anorthosite. We can place an anorthosite to the microscope and we can see that it consists of mainly from anorthite feldspar. And if we must imagine and study the lunar case, sometimes the magma ocean covered the moon after its formation. And from the magma ocean, the feldspars were moving up because they were lighter than the melt, and they formed almost uniform outer shell and crust on the moon. This was shown that this irregularity is proved by the European anomaly all over the moon, all over the rocks. So, if we want to summarize the lunar history according to the lunar rocks, and now is the time to write the exact ages to the Copernican system, we may write 0.8 eon or billion years, to the Eratosthenian 3.2, to the Imbrian bottom 3.9, 4.2, and about 4.5, the same age like that, because the moon was formed from the Earth by an impact of a Martian type. This is the newest model since 1984, but now we deal only with the lunar history. The first period was the formation of the lunar crust, and it was at the beginning, the great melting magma ocean, some 100 millions of years needed, to thicker and thicker lunar crust, and there was another period of melting between 3.9 and 3.2, 3.1. This is the period, the great two periods of magmatic activity we can divide on the moon: anorthositic period and basaltic period. This is for the sake of simplicity to have an overview of the main rock types. Anorthositic crust from the magma ocean and melting of the inner belts in the deep from the mantle produced the lunar mare material. So a longer history of planetary evolution can be seen both in the rocks and in the strata and layers and stratigraphy we could overview in these some moments. Now we go to the Mars. Mars is a similar case to the moon when we see the events. There were Mariner space probes in the 60s. In 64, Mariner 4 and 69, Mariner 9 photographed Mars And the first geologic map of Mars was made from the photography of Mariner 9. We can see the geological map and the details, the two great parts of the Martian surface, the Terra region in the southern part and the lower mare-type northern regions. But this is the case in the early 80s. The map was published in the late 70s, and we may compare these results of the recent studies of Mars Global Surveyor. Mars Global Surveyor had two important instrumentation. One was MOLA, Mars Orbital Laser Altimeter, which allowed to construct this hydrological type map. Here the altitudes are represented, but the lower parts are filled with a kind of ocean, as we can see from the color. And this shows that the northern ocean and great impacts of Argyre and Hellas dominate both in the stratigraphy and in the face of Mars, and the Great Tarsis volcanic block in the left side of the map can be seen that the smaller Elysium volcanic place is determining. Now we see the polar regions. There also you can see the northern polar cap in the center of the northern ocean, and there is a southern cap, and not so deep lakes or seas can be seen in the Mars there. Now, when we go to the Mars, we can imagine the surface material by the landers. Here we can see the Pathfinder vicinity landings landscape, and this landscape is used in our Hungary space experimental robot. Hungary is a Hungarian university surveyor, because we found that the original surveyors 35 years ago, in the same time when Mariner went there, the surveyor probes went to the moon and landed. They took soft landing 1, 3, 5, 6 and 7. They were successful, and we have got the instrumentation from Eugene Schumacher, and we made, now I can show you the Hungary 3 from Szombathely High School, from the college. They made it with radiation, with instrumentation, and that is very important to compare first the landscape, then the rocks. This is an important level: high geology, surface, and the study of the rock themselves, and make some theory of the planetary evolution, the thermal evolution. Here you can see an Apollo large block on the surface of the moon, and now we can study somehow the lunar rocks, and over the lunar rocks the Martian rocks. Why? Because we have Martian rocks by chance, by impacts. Here is a map, here is a picture which shows how a large block came up from a great impact, from a belt where these stresses throw out large blocks of rocks, and we know more than 12 Martian meteorites. And finally, I should like to tell something to the Martian conditions, because these Martian meteorites are very interesting. Martian meteorites are very similar to basalts and very similar to the so-called lerzoids and mantle-like rocks. So they are at the boundary of the similar to the crust of the earth, basaltic tiles, but some of them are rarezolitic, which is the upper part of the mantle, and it is composed from this ancient olivine and pyroxene material. This is very interesting characteristic of the Martian rocks. But there are another aspects of Martian rocks too. They are more oxidized and they contain some carbon in the form of calcite crystals and calcite and dolomite crystals. In dolomite you can see there is magnesium together with calcium, and in these crystals, different levels, we can study the characteristic of the Martian rocks. The deepest level is the smallest. In large, we can see, for example, the chemistry. In the cave of chemistry, we shall find pyrite. In the Martian rocks, calcium carbonate, CO2. We can find characteristic feldspar, more natrium is inside. So there are chemical characteristics of the composition. In a lower level, we can see very special minerals, for example, magnetic crystals. But magnetic crystals are characteristic so, like the magnetotactic bacteria, they form double chains of very regular magnetic crystal, more or less octahedral, and they are 50 nanometer in size, and they form a very regular chain, 50 nanometer space, 50 magnetic crystal, 50 nanometer space. So they are regularly arranged. And in this year, Lunar Planetary Science Conference, Imre Friedman had a study with his group that he could find 13 elements of a chain. Such a large one, so he made the statistics, and this magnetic crystal can be found in the Earth only in the vicinity of this magnetotactic bacteria. Going lower layers, we can see Pach. Pach is a kind of polymerized aromatic hydrocarbons. Polymerized hydrocarbons. This is a fossil of the maybe the remnant of fossilized great molecules may be connected to the life, and this is the level, this is the deepest level even on the chemistry, which can show something from the Martian life, but these levels are can be continued up there because these minerals contain those kind of isotopes, more deep level, isotopic level, isotopes of radionuclides, which represent the content of the atmosphere of the Martian atmosphere. So different levels of hierarchy can show different characteristics of the Martian life. So if we compare the landing site landscape, we can see some river system. When we see the geologic map, we can see that streams formed rivers which were meandering. We can see volcanoes. So it was an active body about 3 billion years ago or 2 billion years ago. Then later, till today, life could survive even in very bad conditions, but they are very similar to the atmospheric conditions up to 11 kilometers and in the bottom of the sea. So the conditions are not so bad in Mars that even today, if there were life, existed life, till today it could survive, and these hierarchy levels show more and more signs of the ancient life. Of course, many other biomarkers can be found in the cave of Mars, but Mars is now in the center of the exploration. So this is only some interesting from the Mars history, but it is important to see that we have also a thin section of a Martian meteorite, and we can study it. And now we can study it and close this study with a summary of the planetary evolution. Now we summarize our cosmic material studies. We make two summaries. One deals with the planetary bodies themselves. If we make a system of time and we make an interval from the beginning of the solar system till today, we shall represent the four bodies in the following way. First is the asteroidal body. Here is the intensity of the transformation and only the sharpness of the asteroidal evolution, not in scale. It is only some 10 millions of years of thermal history. The second one is the lunar history. We told that it has two peaks. One is for the anorthositic, another is to the basaltic volcanism period. When we see Mars, we can see that the Martian history is almost closing, but because of the thermal history contains mainly the ancient events, and we, even if he has bacteria, can survive. The terrestrial history is continuous. So, four different bodies represent four different periods in the thermal evolutionary history. So, asteroids, Moon, Mars and Earth shows a complex picture together. Another one is the thermal history in the solar system. In the solar system, there were two heating up processes. Here is also time, but two main events can be shown. One is the formation of the Sun, another is formation of a planet. Formation of the Sun means that the distance from the Sun was a very important thing. So if something was heated up to the vicinity of the Sun, here is the Sun, it was heated up and went down, and if it was far from the Sun, it was not heated so much up. So this was a very important event, formation of the Sun. Now the second event depended on the body. Larger body heated up more the materials than the smaller body, and we could study this. For example, this is the Earth, and this is at the bottom a kind of asteroid. So this double event can be studied when we study cosmic materials in the solar system, and that's why it is so interesting to have lunar samples, Antarctic meteorite samples, and Martian samples to be compared with terrestrial samples, because this very active, very various history can be compared, and these processes are somehow contain these materials. That's why we invite you to study cosmic materials in 10 sections and then reconstruct the history of the solar system. Thank you.